Hello and welcome to the next edition of Physics 6 Lab. Today we'll be looking at the moment of inertia. Hopefully you have your moment of inertia data page printed out, and we're going to take a look at how we're going to measure that. We have a very fancy, sophisticated little device here to measure the moment of inertia of rotating masses. Just want to refresh your memory a little bit. If you have a point mass, m, revolving in a circle around some center of axis here, axis of rotation, the moment of inertia of a point mass going in a circle of radius r is just capital M r squared. This is the theoretical value for a point mass going in a circle. It's just mr squared. So in this lab, the m, the so-called point masses, will be these little slotted masses that we have here. They are actually able to revolve around a central axis, and we're going to somehow try to confirm that the moment of inertia, we're going to measure the moment of inertia of these masses and confirm that it's close to mr squared. So mr squared is the ideal moment of inertia, and we're taking that to be the theoretical value, which we're going to compare with an experimentally derived value. So how are we going to do that? Okay, what we have here is a rotating shaft with the 2 point masses here, and they're connected to a string. The string is connected to 100 grams, and you can see that when I let go, the 100 grams begins to fall and turns the shaft, causing the masses to revolve. Now the important thing here, we're going to derive an equation for finding this moment of inertia using this device separately from the ideal. And how it works is like this. It's conservation of energy, basically. Notice the hanging mass has a certain height. So what kind of energy are we talking about here? Energy of height, that's potential energy, mgh. So as this thing falls, that potential energy is being converted to kinetic energy. What kind of kinetic energy? Linear or rotational? Well, both. Because two things are speeding up. The falling mass is speeding up linearly, but the rotating masses are speeding up angularly. So we have kinetic energy of rotation and kinetic energy of translation going on at the same time. So we have our mgh is going to equal 1/2 mv squared of the falling mass plus 1/2 I omega squared of the revolving masses. You put that on the board, that's a good starting point. So the mgh of the falling mass, that's the potential energy, is being converted to the translational kinetic energy of the falling mass plus the rotational kinetic energy of the rotating masses. I'm not sure how clearly you can see this, but this says mgh equals 1/2 mv squared plus 1/2 I omega squared. So the unknown in this lab is I. What we want to measure in this lab is the moment of inertia. In order to do that, we need to know the velocity of the falling mass, the final velocity. So it all gets converted into kinetic energy. We need to know the final velocity of the falling mass. So how do we do that? If we just let the mass fall, well, what's velocity? What's linear velocity? It's distance over time, right? So it's going to fall a certain distance in a certain time. We're going to measure the distance, how far it falls. We're going to measure the time it takes. And so the speed, the average speed of that object, velocity, is just distance over time, which is the height it falls over the time it takes. But that's the average velocity. What we want is the final velocity. So is that going to be greater or less? Well, if it started from 0 and went to 5 meters per second, the final velocity would be 5 meters per second. What would the average be? The average would be 2.5, right? Just 5 plus 0 divided by 2. That would be the average. So if I told you that the average velocity was 2.5, how could you get the final velocity? It's just double that, going from 0 to some final value. So the final velocity, V final, is going to be 2h over t. And that's what we're going to plug into here. Now for omega, remember the relationship between r and v? V equals r omega. So instead of omega squared, we can write v over r squared. Plug that into here. And for v, we can use 2h over t. And that'll give us an equation where we can actually solve for I. I'm not going to go through the actual derivation of it for you. It's very simple algebra. But what do we use for r here? Now, this r, in the ideal moment of inertia, this r is the radius of the circle that these things are going around. Your lab instructions call out for 12 centimeters, so I've already pre-measured this to be 12 centimeters from the center of the shaft to the rotating mass. The center of the rotating mass is 12 centimeters. That's capital R for mr squared. But what does this little r stand for? Relating the velocity of the string to the angular velocity of the rotating masses. What's connecting the linear velocity to the rotating angular velocity is the shaft. You can see where the string meets the shaft is the radius of the shaft that we're talking about. So the little r here is the radius of the shaft, which we're going to be measuring with the vernier caliper. So we'll get into that in a moment. So what happens is we're going to release this thing. The falling mass falls a certain height h. We're going to time the time with a stopwatch. And when you solve this for I, you get the expression on your handout. If we solve this equation for I using the substitutions that we just talked about, I is equal to this formula here on your handout. M, that's the falling mass, times little r squared times gt squared over 2h minus 1. Now, it's a little bit ambiguous on your handout. Actually, that's 2h minus 1. Here we go. So what it really means is we've got the gt squared over 2h altogether minus 1 times little m, little r squared. These things we can measure, the height, the time. The little r we'll measure with the caliper. The hanging mass we know is 100 grams. And depending on the time it takes, we get a moment of inertia. The longer time it takes, the bigger the moment of inertia, because when the moment of inertia is high, it's harder to get it going and takes a longer time to hit the floor. So this makes sense. So that's the formula we're going to use to calculate the moment of inertia experimentally. Ideally, the moment of inertia is capital M, capital R squared. We're going to compare those two results with a percent error. So let's just jump right in and start measuring the things that it tells us to measure. If you look at page 2 of your handout, it says to measure and record the following data on the data page. The first thing is h, the distance that the falling mass is going to fall. Well, that depends on where we release it. So it's really important that we release it at the same point, exactly the same point each time. That could be a source of measurement error, not releasing it at exactly the same point. It's going to be a matter of judgment. So I'm going to, looking at the bottom of this thing, I'm going to try to release it at exactly I'm going to try to release it at exactly 75 centimeters each time. So on your data page, you need to record page 3, where it says h, the distance in centimeter, the distance that m falls, we're going to record that as 75.0 centimeters. The mass of the falling mass is just 100 grams. Now the radius of the shaft, we need to measure that with the vernier caliper. So I'm going to take the vernier caliper and just clamp it onto the shaft, and then we can read that value. Now this gives us the diameter, of course, the diameter of the shaft that's being measured by the caliper. So that's going to be, I don't know how sharp this is for you, but it looks like we've got our pointer here is pointing between 1 and 2. Looks like 1.3. I'm going to have to look at this closely. No, it's about 1.29. Yes, 1.29 centimeters. That's the diameter. 1.29 centimeters. So you can write that. There's a space for that on your data page. It says diameter of the shaft, 1.29 centimeters. So the radius will just be half of that. So we'll just divide 1.29 by 2, and we get 0.645. 0.645 centimeters. And we really need to round that off because it's not accurate to a thousandth of a centimeter, so we're going to call that 0.65 centimeters. So the radius of the shaft, 0.65, sorry, 0.65 centimeters. Okay, so Rm, R centimeters, the distance of the rotating masses from the center of the shaft. I've already measured that, as I pointed out, from the center of the shaft to the masses is 12.0 centimeters. So you can write that in to your data page, 12.0 centimeters, like so. Okay, so we've measured those things. Procedure 1 says place the mass hanger. Now here's the deal. Okay, we're going to be measuring moment of inertia of something. Moment of inertia of these two little masses. But there's also other things that are rotating here. This rod with the clamps. I don't know if you can see this or not. Let me show you a little bit closer view of this. These are the masses here, but look at there's these wing nuts, and the rod itself, and the shaft. They're all rotating too. Don't they have mass? Don't they have moment of inertia? Of course. So, but what I want is the moment of inertia of just these two masses by themselves. So what we're going to do is remove those two masses to start with, and just work with this structure here of the crossbar and the shaft and the wing nuts. We're going to measure the moment of inertia of those things alone. Then later we're going to add the two masses and get the moment of inertia of that combination, and then we'll subtract the masses by themselves. You can see on your data page where it's set up for that. We're going to start out with 0 masses on the system and measure the time for that. Then we're going to add 50 grams, measure the time for that, and then later we'll subtract the system alone from the total of the masses plus the system. We're going to subtract the system alone, which is this moment of inertia, and that'll give us the moment of inertia of the masses alone. So here's the total moment of inertia minus the system. This is the system here by itself with 0 masses. Later we'll put the 50 grams on, measure its moment of inertia, and subtract. And that'll give us the moment of inertia of just the 2 revolving masses. By the way, because we have 2 revolving masses here, we're going to have to put a 2 here in our ideal expression. For the ideal moment of inertia, just 2 mr squared because we have 2 masses going around. Okay, so let's follow the instructions. We've removed the 2 individual masses. And we're going to release the 100-gram mass, letting it descend downward, causing the system to rotate. All right, so let's wind this up. I better come around to the front so I can see the meter stick clearly. I'm going to time it with my cell phone clock. I'm going to set it at the 75 centimeter mark at the bottom of it. Then I'm going to release it and start the watch at the same time. And go. I have to be careful to stop it at exactly the point it hits the ground. You can't see that, but that's what I did. So now I'm getting a time of 7.46 seconds. So we need to write that time. That's T1, 7.46 seconds. And we're going to do it another time. It asks for 3 trials, but I'm just going to do it twice for the sake of this video not being too long. And that way we can be sure that it's in the ballpark. Starting at 75 centimeters. Probably blocking your view here. Sorry about that. And I'll release, start the stopwatch. This is how labs really go. And start. I'm going to be really careful. Stop it just when it touches the ground. Got it? I'm getting 6.96. Last time we got 7.4. So that's a measurement error of about half a second, which is fairly large, but that's what it is. 6.96. And let's do it a third time, just to see if we can get a reasonable average here. Starting at 75. Start. Got it? That was 7.45 seconds, which is very close to the first value. We can take an average of those 3 to get the average time. So that will give us the moment of inertia. We can immediately plug those numbers in get the moment of inertia of the system alone without the point masses going around. So obviously the next step will be procedure 2, which is secure 50 gram slotted masses to each end of the rod, 12 centimeters from the center. I've pre-measured this out, 12 centimeters. And the first thing you're going to notice, of course, is that when we release the hanging mass, watch this, notice how much slower it's going. Why is that? Because we've got the masses there, it's got more inertia, there's more moment of inertia, and so it's going to take longer to do it. So procedure says, repeat the procedure 3 times, record the times in the column under 50 grams. Okay, so that's easy enough. I just do the same thing over again. It's going to take a little bit longer this time. Reset the watch. Release the hanging mass from the 75 gram mark. "75 centimeters, I mean. And start. I'm going to be really careful this time to touch it just as it hits the ground, which you can't see. Boom. Okay. I'm getting 10.81 seconds. So we're going to record that. Now we have 50 grams hanging from the hanger. So we're going to record that time as 10.8 seconds for our time T1. Let's do it another time to get an average. Loop because our string broke for some reason last time. We're not taking into account the weight of the string here either. It's very minimal, but that's a possible source of measurement error. Take it up to 75. I think I'm just going to do this one twice if the two measurements are close. That'll save us a little bit of time for the video. All right, marks, set, start. Again, this is just with the 50 grams revolving. Okay. Something happened here that kept it from hitting the floor. It didn't hit the floor. It stopped before hitting the floor because the string got tangled here. Now this is good. This is why we do these things, so you can see the kinds of difficulties that face real experimental physicists in trying to take measurements. Taking measurements in a lab is not easy. There's always some little glitch that shows up that you didn't expect. And that's one of the reasons we do these labs, so you can be familiar with lab procedures. I'm going to do this again, starting at 75 because it didn't hit the ground, because the string was tangled. So let's do it again. Go. We'll see how close. Last time it was 10.8. We'll see how close it is this time when it hits the ground. Boom. Okay, 10.7. All right, I'm impressed. That gives me confidence that we can record 10.7. And I'm not going to bother to take another data point. We'll just use these two and take the average of those two for the 50 grams. Next, we're going to replace the 50 grams with 100 grams. You can see the trend of what we're doing here, right? 50 grams off, put 100 grams on. I'm going to try to unwind the wing nuts equally so the center of our mass stays 12 centimeters from the center of the rotating shaft. Let me just verify that. 12 centimeters, 12 centimeters. So what's going to happen now? It's going to rotate slower or faster. Obviously, it's going to rotate more slowly because it's got a greater moment of inertia. So from this point, I think I have confidence in our timing mechanism. I think we'll just take one measurement for each of these following masses. For the sake of brevity of the video. Starting at 75 centimeters. Turning on my cell phone. Reset the watch. And I keep getting an ad, which is a disadvantage of using your cell phone. Hang on a second, we'll get there. Stopwatch, reset. Okay, here we go. Ready, set. Whoops, I started by accident too soon. Gonna reset that. Ready, set, go.